Hi everyone, we are Yusuf Al-Naber, Aziz Abdelal, Nader Mahmoud, and Sikhen Williams. During this video, we will be discussing why volcanic eruptions cause visible propagating shockwaves. We came across this observation throughout these two videos, because you can visibly see the shockwave growing after the volcanic eruption. After our observations, we came to a hypothesis that the shockwave is visible to the naked eye since it induces a change in the density of the surrounding air, which in return distorts a light reflection.
When a volcano erupts, a large amount of energy is deposited. This energy gets carried by the surrounding air molecules to form a supersonic wave called a shock wave. This shock wave causes an area of pressure to expand spherically outwards from the core of the volcanic eruption. The abrupt propagation of pressure naturally triggers the change in the density of the surrounding medium.
As illustrated in this figure, the angle of incidence of light as it passes through the interface from the density of one medium to another changes the refractive angle due to the refractive index. This change of density will cause a change in the refraction index. The index of refraction, which is labeled n, is a ratio of the speed of light in a vacuum to the speed of light in a medium, which in our case is air. To calculate the refraction index, we use the formula n equals c over v, where n equals the refraction index, c is our velocity of light in a vacuum, and v is the velocity of light in a medium. The factors that affect the refractive index are density, temperature, and pressure. Therefore, since there is a sudden change of density in a medium, this causes a change in the refractive index in the medium. As the air molecule compresses, this will cause an increase in the density of the medium, which will change the refraction index, which then will be seen in the visible wavelength. A good example is trying to pick a fish up with your bare hands in a pond. The position of your hands and the fish appear at a different position from the actual spatial relation once your hands enter the water.
The hypothesis of a change in density inducing a visible aberration accompanying the propagating shockwave is confirmed. The deposit of a large amount of energy within a short time span in a compressible fluid causes a shockwave. Within the shockwave, the density of air is increased with relation to the surrounding bulk air due to a drastic increase in temperature and pressure of the air molecules. At the boundary of the shockwave, there is an abrupt change in density which causes a discontinuity of the path of light waves. The change in pressure, density, and temperature changes the refractive index of air in the shockwave when compared to the surrounding air. Therefore, the change in refractive index of the compressible gas distorts lights and creates a lens, which has the same effect of the example of your hand position within a pond.